Morning. Welcome to this session on CPU scheduling in operating systems. So these are the things we will be discussing in this video regarding the basic concepts of CPU scheduling, the scheduling criteria, the various scheduling algorithms, and what is thread scheduling, what is called as multiprocess scheduling, what is real-time CPU scheduling. So these are the objectives of going through this video. So before seeing the various CPU scheduling algorithms, we shall see what are the basic concepts relevant to CPU scheduling. So what is the first aim of operating system is it has to have maximum CPU utilization obtained. The OS is responsible for various scheduling activities, out of which one of the aim of the operating system is to obtain or attain maximum CPU utilization. That is, you don't want the CPU to be idle, it has to be given some work to do without any idleness so that it can achieve maximum CPU utilization. So how to attain maximum CPU utilization is using the programming concept of multi-programming. What is multi-programming? At the same time, multiple processes will be given to the CPU for execution. Next, CPU and IO burst cycle. What is the term CPU and IO burst cycle is? It consists of process execution, consists of cycle of CPU execution and IO wait. The term CPU IO burst cycle indicates the total process execution will consist of cycle of CPU execution followed by input output waiting for some input output operation to be taking place along with the process execution with the CPU cycle. This is what the burst cycle, entire burst cycle called as CPU IO burst cycle is termed as. Next, CPU burst followed by IO burst. So the distribution of CPU is the main concern of this scheduling algorithms. So when you see this diagram, some of the instructions are keep on executing like load, store, add, store, read from file, and in between there is a interrupt for wait and IO operation. So whatever load, store, add, store, read from file, that we call as CPU burst. Whatever time spent for waiting for IO operation, that we call as IO burst cycle. Again, store, increment, index, write to file, this comes under the CPU burst. Again, waiting for an IO is called as IO burst. Like this repetition of CPU burst followed by IO burst will be taking place during any process execution. Our aim is to have maximum CPU burst. So the maximum CPU utilization, achieving maximum time utilized for CPU. So just an histogram diagram showing the CPU burst times. So the x-axis has burst duration given in milliseconds. Y-axis has the frequency of occurrence of CPU burst times. Okay. This just graph indicates a CPU burst times. If you want the CPU burst time or CPU utilization to be more. next one, CPU scheduler. What is CPU scheduler? So you have short-term scheduler, medium-term scheduler, and long-term scheduler as discussed in the previous video. Now, short-term scheduler, what is the role of short-term scheduler? It selects from among the processes in the ready queue and allocates the CPU to one of them. So the role of short-term scheduler is to select a process already saved in the ready queue, and it has to give the CPU to one of such process taken from the ready queue. So the process in the queue may be of various orders. It may have any order, but one process will be selected by the short-term scheduler for giving the CPU. How CPU scheduling decision takes place? CPU scheduling decision may take place when a process switches from running to waiting state, switching from running to ready state, switches from waiting to ready state, or the process terminates. When and all you have to go for this CPU scheduling. It depends on these four things. What are the four things is, whenever a process switches from running to waiting state, that means during that time the CPU will be idle, so it can be given to some other process for execution. That is one thing. The second thing, whenever a process switches from running to ready state means, so from the ready queue I can take one process and I can give this process the CPU. So during that time CPU scheduling may be necessary as to which process to select from the ready queue. Then whenever a process switches from waiting state to ready state. So whenever a process is ready to be executed, it will be put in the ready queue. During that time, whether it has to be selected or not is decided by the CPU scheduling. And whenever a process terminates, that means the CPU and allocated resources are free now, so they can be given to some other process. So during that time, the CPU scheduling decision may be essential. And out of these four things, scheduling under 1 and 4 is non-preemptive. What is the term non-preemptive? Is whenever a process that are executing under the criteria 1 and 4, they cannot be preempted, they cannot be stopped or suspended in between, and the CPU can be given to some other process. When processes are executed in first criteria and the fourth criteria, definitely it will be executed as non-preemptive process. Non-preemptive in the sense the process execution cannot be halted or suspended in between while the process is executing, so that the CPU can be given to some other process. This cannot take place as a non-preemptive scheduling. But the process executing under other two criteria, that is under 2 and under third criteria, can be executed as both preemptive and non-preemptive. Preemptive means you can stop or halt or terminate the process or suspend the process which is executing using the CPU in between, and you can assign the CPU to some other process, maybe based on some priority. So that is what preemptive scheduling. So preemptive scheduling can be done for these kinds of process. When a process is accessing shared data, when a process want to execute in kernel mode, it can the process which is executing currently can be terminated or preempted, and can be the CPU can be assigned for kernel mode process. Similarly, whenever there are any interrupts occurring which the OS has to immediately take care of, during that time the CPU can follow preemptive scheduling. Next one, dispatcher. So what is this dispatcher going to work? Dispatcher module gives control of the CPU to the process selected by the short-term scheduler. So what is the role of dispatcher is? It is the one who is going to give the control to the CPU whenever a process has been selected by this short-term scheduler. To that process, the control of the CPU will be provided by this dispatcher. What is giving the control of the CPU involves means switching context. So the state of the current process has to be saved, and has to be saved in the PCB, that is process control block, and the control has to be given to the newly selected process from the ready queue by the short-term scheduler. So during this switching time, you have to save the previous old context and you have to take the new context. Context in the sense the data from the PCB, process control block. Then switching to user mode. So when it is obviously executing the kernel mode, the control has to move to the user mode. Then jumping to the proper location in the user program to restart the program. So whenever the control is given back, the location of the user program has to be restarted properly. Has to be restarted properly, exactly moving to the correct location of the program. That is what the dispatcher does. All these activities will be controlled by the dispatcher whenever a process is given the control of the CPU. Next terminology is dispatch latency. It is the time taken for the dispatcher to stop one process and start another running. The time spent by the dispatcher module to stop one executing process and give the control to the new process. That is what dispatch latency. Next, whenever your CPU is going to follow any scheduling, it has to take care of all these scheduling criteria. The OS has to take care of all these scheduling criteria whenever a CPU scheduling decision is taken care of. First one, CPU utilization means keep the CPU as busy as possible. The first important thing is we must keep the CPU as busy as possible. The meaning is we should not leave the CPU idle. Second, throughput. Throughput is nothing but number of processes that complete their execution per unit time. So if you measure a unit of time, for example, take 1 hour duration from 9 to 10 a.m., how many processes has been executed by the CPU? The count we call as the throughput. We want the throughput to be more. A number of processes that completed their execution during that 1 hour duration. For example, that is what meant as per unit of time. Waiting. Next one, turnaround time. The amount of time to execute the total amount of time to execute a particular process. Next, waiting time. The amount of time a process has been waiting in the ready queue. That is the amount of time a process spent waiting in the ready queue before it is assigned the CPU for execution. That is what called as waiting time. Then response time. amount of time it takes from when a request was submitted until the first response is produced, not the output. Response time is the amount of time spent whenever process request has been generated until the first response for that process is generated back. Not the complete execution, only the first response given for that particular process when a process makes any request. That is what called as response time. It does not indicate the complete time for giving the output, but the first response provided to that process by the CPU or for any other device or from any other device. That is what called as response time. So these are the scheduling algorithm optimization criteria. Maximum CPU utilization, we want maximum throughput, minimum turnaround time, minimum waiting time, and minimum response time. Keeping all these criteria, the scheduling algorithm has to be selected or has to be carried out. So you have various scheduling algorithms. The first algorithm is first come first serve, or in short called as FCFS scheduling algorithm. So take a process and the burst time for the process which is shown here. There are three processes in this particular example which is named as P1, P2 and P3. The burst time of a particular each process has been given. Burst time is nothing but the time spent for execution by that particular process using the CPU. So for P1 it is 24, P2 it is 3, P3 it is 3. So now you want to draw a Gantt chart to decide what is the total turnaround time, what is the waiting time, and what is the response time. We want the turnaround time to be minimum. So what is the final turnaround time given when you apply this FCFS scheduling algorithm? FCFS means whichever process comes first into the ready queue will be assigned the CPU first. Will be assigned the CPU first. It is nothing but suppose we are waiting for buying any ticket in a railway station or buying any ticket in a cinema theater. Whoever enters the queue first will be taking the ticket first. The same as that, this FCFS algorithm is going to work. The very common example what we see is buying ticket in a ticket counter, maybe for a cinema theater or for a railway ticket reservation system. Whoever enters the queue first will be given the ticket first. So keeping this example in mind, now we will try to solve or find out the total turnaround time for this particular scheduling algorithm for these three processes. First step is you need to draw the Gantt chart showing the burst times of each process. So your starting time begins with 0. Your P1 is entering the ready queue first, so P1 has to be assigned the CPU, taking total 24 milliseconds. Okay, then P2 is given 3 seconds. P3 is assigned the CPU 3 seconds. So P1 will be completing its execution, it will leave the CPU, then P2 will be assigned, then it completes its execution, then P3 will be assigned. Now you have to calculate the waiting time and average waiting time for this. What is the waiting time for P1 is, on seeing the Gantt chart we can decide the waiting time for P1 is 0. What is the waiting time for P2? It is 24. P3 it is 27. Now you have to find out the average, means you have to just add all the waiting times, follow and divide by 3 as the total number of processes 3. So you get the average waiting time as 17. Next, suppose the process arrive in the order P2, P3 and P1, means now during this time you have to assign the CPU for P2 process first, then P3, then P1. So taking this order, if you draw the Gantt chart, P2 is assigned, means the burst time for P2 is 3. So 0 to 3. Then P3 will be assigned as per the arrival order. So then after 3 milliseconds, means it will be using the CPU up to 3 milliseconds. So when the time is 6, it will leave the CPU. Then after that, P1 will be assigned the CPU. So it has to spend 27 milliseconds. So at the time 30, P1 will be completing its execution. Now here also you are going to calculate the waiting time and average waiting time. Waiting time for P1 is 6, P2 is 0, P3 is 3. Average waiting time is 3. Actually, the average waiting time during the second or arrival order, it is reduced. It is reduced. It is very much better than the previous case. So from this, what we are learning is, we are learning an effect called as convoy effect. The meaning is short process behind the long process. If you are following the arrival order in the first case, even though P2 and P3 request shorter burster time than P1, they are spending more waiting time as more than the time needed for the CPU. P2 and P3 actually requires only 3 millisecond time for execution, but they are spending more time rather than their burst time requirement. This is because the reason is they are arrived after the longer burst time process. So process, when you are having process of this nature, we call this effect as convoy effect, that is keeping shorter process in terms of burst time behind the longer process will lead to more waiting time for the shorter process than necessary burst time. So that is what called as convoy effect. So the example for this is one CPU burst and many IO bound process. One CPU bound means the process will be spending more time for CPU execution. IO bound process means the process will be spending more time for IO operations. So when you have mix of CPU bound and IO bound, definitely it leads to effect called as convoy effect. Shortest job first scheduling algorithm. So to remove the disadvantage of convoy effect, next they introduced an algorithm called as shortest job first scheduling algorithm, in short called as SJF. Here, each process is associated with each process the length of its next CPU burst. Using this length of the CPU burst, you are going to assign the CPU to the process with the shortest burst time. SJF is optimal. Optimal in the sense it gives minimum average waiting time for the, what is the advantage you are getting out of the shortest job first algorithm is the minimum average time waiting time will be reduced compared to first come first serve scheduling. But here also you are going to have a disadvantage. What is that is you must know the burst next burst of the next process. Without knowing that, we can't decide which is the shorter process. So knowing the length of the next CPU request is a difficulty with respect to shortest job first. So how to know this? Every time you have to get the burst time from the next user or next process. Then only you can decide which is the shortest burst, shortest job. So example for shortest job first. Again take some 4 process here with the burst time given. So you have 4 process P1, P2, P3, P4 and the corresponding burst times for the process are given as 6, 8, 7 and 3 respectively. So you are going to draw the scheduling chart, otherwise called as Gantt chart, showing the burst time and the waiting time for each process in the form of a queue. Now you are not going to follow the arrival order. You are not worried about which come first or which come next and all. You are going to check the length of the burst time and you are going to assign the CPU to the process whichever is having the least burst time requirement. Out of these 4 processes, when you observe, you can easily know P4 is having the minimal burst time or length of the burst time is less compared to all other process for P4. So P4 will be given the CPU first. So totally it will be taking 3 milliseconds for completing its execution, then it will leave the CPU. And the next again, out of the available 3 process, now you have to again compare and check which is having the least burst time requirement. Again you can see P1. So P1 will be given the CPU next. So it will be executing up to 6 milliseconds and it will leave the CPU after 9 milliseconds as 3 plus 6 will be 9. Next, there are 8 and 7. So 7 is the minimum which is for P3. So P3 will be given the CPU next. So 9, at the time 9, P3 will be assigned the CPU and it requires 7 milliseconds. So 9 plus 7 at the time 16, during the time 16 it will leave the CPU. Then the last end process which is P2 will be assigned the CPU taking 8 milliseconds as the burst time. So when it is given at the time 16, so 16 plus 8 totally during 24th millisecond the process process P2 will leave the CPU. Now if you find the waiting time and average waiting time, you can find the waiting time of P4 is 0, waiting time of P1 is 3, P3 is 9 and P2 is 16. Average waiting time, you just add up all the waiting times and divided by 4 as the total count of processes 4. You get the average waiting time as 7. Now in this case of SJF, we need to know the next length of next CPU burst. How to estimate that? you can only estimate the length. It should be similar to the previous one. Then pick process with the shortest predicted next CPU burst. Can be done by using the length of previous CPU burst using exponential averaging. So here deciding the length of next CPU burst can be done just by predicting the process with the similar burst times. It may be, sometimes it may be wrong or sometimes it may be right. Using exponential averaging, you are just going to decide the next CPU burst and you have to find out the length of the next CPU burst and assign the CPU here. And another version of this SJF is shortest remaining time first. Shortest remaining time first. It is a preemptive version of SJF. Next, a graph shows the prediction of the next CPU burst, how it is predicting. So the x-axis shows the time, burst time, y-axis shows the guess, y-axis shows the guess. And just based on the guess, they are drawing a graph showing the length of next CPU burst. Examples of exponential averaging technique to find out the next CPU burst. So based on the recent history, it is the exponential average technique is calculating. And the preemptive version of SJF, we said shortest remaining time first. We will see an example for this case also. So you have process and you are going to get the burst time followed by arrival time in this case. So here you have 4 process P1, P2, P3, P4. The burst time is given in the arrival time is given in the second column as 0, 1, 2 and 3. The burst time is given as the third column, which is 8, 9, 5. Okay, the Gantt chart is shown here. So the process P1 is arriving during the time 0, so it is given the CPU first. So it has been executing up to 1 millisecond. During first millisecond, that is during the arrival time 1, the process P2 is arriving. Process P2 is arriving. So it is, the P1 is preempted and it is given the CPU as the burst time for P2 is less compared to P1. So during the arrival time, so up to 4, the burst time of P2 is 4 milliseconds, which is less compared to P1. So it is given the CPU and it completes the execution. After 50 millisecond, P4, which is arriving during the time 3 and which is having the least burst time compared to P3, it is given the CPU up to 5 milliseconds. So then after this, which is having the shortest least burst time, remaining time, P1 is already executed for 1 millisecond, so the remaining time for P1 is 7 milliseconds. The time required for P3 is 9 milliseconds. Out of this, which is having the shortest remaining time, P1. So P1 is given the CPU up to 7 milliseconds. After this, P3 is given the CPU up to 9 milliseconds. And now if you find the average waiting time for this, it will be less compared to the SJF version. Next one, priority scheduling. So priority scheduling, a priority number will be associated with each process. Based on this integer number, your CPU will be scheduling the process. The CPU is allocated to the process with the highest priority. The meaning is whichever smallest integer we call as it's the highest priority. Whichever process is associated with the smallest integer value, that process will be taken as the highest priority process. Here also you are going to have preemptive version and non-preemptive version. So SJF is priority scheduling, where priority is the inverse of predicted next CPU burst time. So example of priority scheduling, you have process, you have burst time, and you have priority assigned with each process. So P1, P2, P3, P4, P1 is 10 burst time, P2 is 1, P3 is 2, P4 is 1. And the priority is assigned as 3, 1, 4, 5. Out of this, which is having the highest priority is the number which is having the process which is having the smallest integer will be given the highest priority. So out of this, 1 is the smallest integer of the priority which is assigned to P2. So P2 will be given the CPU first. So it will be completing its execution. Then which is having the highest priority is P5. So P5 will be given the CPU next. Next, which one is having P1? Next P3. Next P4. Okay. Next one. So the previous case, after assigning the CPUs, the average waiting time, if you can calculate and check which is whether it is having the least average waiting time or it is more than the previous two algorithms. Round robin, or in short called as RR. Here each process gets a small unit of CPU time called as time quantum Q, usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. Here your RR is going to work as a preemptive scheduling, meaning is every process will be given a fair share of the CPU for a particular time quantum. Like a circle, every process will be given the CPU, reducing the average waiting time. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU time in chunks of at most q time units at once. No process will be spending waiting more time in the queue. So we'll see the example here. So taking the time quantum as 4 means every process in this particular scheduling will get a time slice of the 4 of the total CPU burst time essential to that process. Here you have three processes P1, P2 and P3. P1's total burst time is 24, P2 requests 3, P3 requests 3. Now P1 will be assigned the CPU for total of 4 milliseconds. Again the CPU will be given to P2 which is 3 milliseconds, but actually it requires 4. It will be given 4 time quantum, but the total burst time essential by P2 is 3. So it will execute up to 3 milliseconds and it will leave the CPU. Again it will be given to P3. Here also the burst time is lesser than the time quantum, so it can complete its execution during with 3 milliseconds itself and it will leave the CPU, and the remaining time to the quantum of 4 milliseconds it will be assigned to P1 and it will be completing its execution. So here an example showing time quantum and context switch time is given here. So you have a process. The process time is 10 milliseconds. The quantum is 12. The time quantum given for this process is 12. When it has to switch during that time, 0. Next, the second case, the time quantum is 12, but the process time is 10. The time quantum is 6 means it will stop up to 6. Context switch time will take place at time duration 1. The first case, you don't require any switching. So the context switch is 0. No switches essential in the first case as the process time is 0 but the time quantum is 12. Within the 12th time quantum, because the process time is less than the time quantum allocated for that process, within 10 milliseconds itself it will complete and it will leave the CPU. There is no need for context switching. So the context switch is 0 here. The second case, the time quantum given for this process is 6, but it is taking essential time duration for the burst time is 10 milliseconds. So here it will be taking a one switch. The reason is because the time quantum is 6, after executing 6 milliseconds, the CPU should be given to some other process. So there will be context switching taking place. One context switch is essential for execution of the remaining 4 milliseconds of this process. Third case, the quantum is given as 1, but the time burst time essential is 10 milliseconds, means totally 9 context switches will be essential for complete execution of this process. Every one quantum context switching will take place. The turnaround time varies with the time quantum. A graph showing this particular concept is given here. You have process and you have the burst time given over there. So the thing is, your overall turnaround time should be minimum. Even though if you follow this quantum concept of round robin scheduling, we want the average turnaround time should be minimal for each process. Next one, multi-level queue scheduling. So here, ready queue is partitioned into two separate queues. What are the two partitions is foreground interactive background batch process. The interactive process and all will be kept in the foreground. Batch process will be kept in the background. The corresponding interactive process will always be assigned to the foreground of the ready queue. The corresponding batch process coming from the disk will be given to the background portion of the ready queue. So the particular process will be assigned to that particular partition. Each queue has its own scheduling algorithm. Out of these two partitions, each can follow its own scheduling algorithm. Usually the foreground process or the interactive process will be following RR scheduling. The background process will be following FCFS scheduling. And the scheduling must be done between the two queues. A diagram showing this is shown here. So the lowest priority process are kept as student process, batch process, interactive editing process, interactive process and system process. Priority follows from the top to bottom. The lowest priority process are kept at the bottom, highest priority process kept at the top, that is in the foreground. Lowest priority process kept in the background. Here the system process receives the highest priority, whereas the student process receives the lowest priority. Next type of scheduling is multi-level feedback queue scheduling. Here a process can move between the various queues. You have two partitions. In the previous case there is no movement between the various queues. In this case the process can move between one queue to the another queue. Multi-level feedback queue scheduler is defined by the following parameters: number of queues, scheduling algorithms for each queue, method used to determine when to upgrade a process, method used to determine when to demote a process. So you can move the process between the various foreground and the background queues. This is decided by the need. This is decided by the need. If you want a process to run in the highest priority, you can move that process from the lowest priority to the highest priority foreground. If you want a process don't want to run in the foreground, you can just move it to the batch or background process. This is done with multi-level feedback queue scheduling algorithms. Example, you have three queues, Q0, Q1 and Q2. Q0 is following RR scheduling with time quantum 8 milliseconds. Q1 is following RR time scheduling with 16 milliseconds. Q2 is following FCFS. So here Q0 and Q1 are the foreground queues. Q2 is the background queue. As you are applying this feedback, so if you want to move a process from quantum 8 to quantum 16, you can do that. Or if you want to move a process from quantum 16 to FCFS, you can also do that. How scheduling takes place here. An example is shown here. A new job enters Q0, which is served FCFS. Which is served FCF. When it gains the CPU, job receives 8 milliseconds. If it does not finish in 8 milliseconds, this job is immediately moved to Q1 for 16 milliseconds. At Q1, job is again served FCFS and received 16 milliseconds time quantum. If it still does not complete, it is preempted and moved to Q2. So this can repeat for all the process. Next one, multiprocessor scheduling. It is more complex when you have multiple CPUs to be scheduled. Multiprocess scheduling means here you are not going to have a single CPU, here you are going to have multiple CPUs. Now the scheduling becomes complex, so has to be scheduled between the multiple CPUs. So here you have homogeneous processors within a multiprocessor. Same type or same kind of CPUs joined as a one. We call it as a homogeneous process. Next, asymmetric multiprocessing means only one processor can access all the system data structures. It can share the data. Symmetric multiprocessing means each processor is self-scheduling. Each processor is self-scheduling here in the case of symmetric multiprocessing. And to show this, you have NUMA and CPU scheduling diagram. So for multiprocess scheduling here, so you have a computer, you have two CPUs as multiprocessor. So you have CPU in the left hand side and CPU in the right hand side. The memory can be accessed very faster between the CPU and the memory. But when it comes to when one CPU wants to access of the memory of the another CPU, it may be taking some access time more. So the slow access can happen. So when you want to schedule process between various CPU, it will take some time. When you want to follow multiprocessor scheduling, you have to take care of some of the concepts. First one is load balancing. So in symmetric multiprocessing means all processors will have their own schedulings algorithms. So you have to keep all the CPUs loaded. You cannot leave one CPU idle and one CPU should be working more. There should be a balance between the various CPUs when they are connected in symmetric fashion. Load balancing attempts to keep workload evenly distributed. Next, push migration. Next concept with respect to multiprocess scheduling is push migration. What is this? Is periodic task checks load on each processor, and if it found and if found pushes task from overloaded CPU to another CPU. So push migration concept means there is a periodic checking on each processor. Whenever a processor is found to be overloaded, some of the tasks from that processor will be distributed among the processes which are idle, so that the load get balanced. Then pull migration, the idle processors pulls waiting task from busy. So here the processor itself pulls some process without waiting by themselves. That is called as pull migration. To achieve load balancing, push migration and pull migration is done. Next, multi-core processors. So apart from multiple processors, now you are having multiple cores within a single processor. The trend is to place multiple processor cores on same physical chip. So here it will be faster when you apply multi-core processors. It will consume less power. Multiple threads per core multi-threaded scheduling can take place in these types of processors. How it is taking is takes advantage of memory stall to make progress on another thread while memory retrieve happens. Here, when one process is waiting for memory, during that time it can be spent for other process. Like this, it is used or followed in multi-core processors. So to show this, again you are taking a diagram to show multi-threaded multi-core system. So here C indicates a computing cycle, M indicates a memory stall cycle. Memory stall cycle means during that time some data is essential from the memory. The time spent for that we call as memory stall cycle. So one thread is currently executing, it is spending CM alternately. Next, thread 1. Okay, thread 1 is spending compute cycle, memory stall cycle. Thread 0 spends the time for computing cycle. And when thread 0 spends the time for memory stall cycle, what happens immediately? Thread 1 begins its execution. During the memory stall of thread 0, thread 1 will spend that time for compute cycle. When thread 1 goes into memory stall cycle, the time will be taken by thread 0 for compute cycle. Like this, alternate execution of various threads can take place, spending the or taking the advantage of memory stall time for proper usage for compute cycle. Like this, you can achieve faster access in multi-core, multi-threaded systems. Next one, real-time CPU scheduling. It can have multiple challenges. So you have two types of real-time systems, soft real-time systems and hard real-time systems. What is soft real-time systems? No guarantee as to when critical real-time process will be scheduled. There is no guarantee in the case of soft real-time systems that compulsorily it will be given the CPU. There is no guarantee that compulsorily a process will get the CPU when they are executed in soft real-time systems. Hard real-time systems is compulsorily the process will get the CPU during its critical task execution. So suppose some task T is running, there is an occurrence of an interrupt. So when an interrupt occurs, immediately the interrupt has to be handled. So first, what type of interrupt it will determine. So if it is essential context which will take place and it will execute the interrupt service routine. The time spent for this interrupt occurrence and interrupt service routine beginning we call as interrupt latency. Conflict phase of dispatch latency. When there is interrupt latency, dispatch latency may also take place. There will be a conflict between the dispatch latency and the interrupt latency. When there is dispatch latency occurring, preemption of any process running in the kernel mode, during that time dispatch latency can occur. Released by low priority process. So during real-time CPU scheduling, it has to take care of interrupt latency as well as dispatch latency. So dispatch latency in example diagram shows this. There is an occurrence of event. When an event occurs, there should be some response to that event. In between this response time, the interrupt may be processing or some dispatch latency may be occurring, or maybe some conflict between various processes. Then maybe some real-time process execution take place. All these should be taken care of during any event execution. Next one, priority based scheduling. For real-time scheduling, scheduler must support preemptive priority based scheduling, but only guarantees soft real-time. For odd real-time must also provide ability to meet deadlines. So this can be achieved with priority based scheduling for odd real-time systems. Next one, rate monotonic scheduling. A priority is assigned based on the inverse of its period. Shorter periods will get higher priority, longer periods will get lower priority. So obviously the higher priority process will be executed faster than the lower priority process. It depends on the burst time. Whichever process having least burst time will be given higher priority. Whichever process having larger burst time will given lower priority. Diagram showing the missed deadlines and rate monotonic scheduling. Here you have earliest deadline first scheduling algorithm for this rate monotonic scheduling. Priorities are assigned according to their deadlines. The earlier the deadline, the higher the priority. The meaning is whichever is having shorter periods will get higher priority. The later the deadline, it will be given the lower priority. Real time means within the stipulated time a particular process should be completed. That stipulated time we mean here as deadline. So if your deadline is least, then it will be given higher priority. If your deadline is more, it will be given lower priority. That is what earliest deadline first scheduling algorithm. Next scheduling is proportional share scheduling. Here the time shares are allocated among all the processes in the system. There will be a fair sharing of the time among all the processors. Each process will get n by t of the total